In this question, we'll be solving a polynomial inequality. The polynomial we're looking at begins as 3x to the power 3 minus 3x squared minus 2x, which is less than or equal to 2x cubed minus x squared plus x. First step is get everything to the left side. So let's subtract 2x cubed from both sides. Could have put it on the right side, but whichever you prefer. I'm going to move everything left, so that gets rid of this 2x cubed on this side. Do the opposite of minus x squared, that's plus x squared, so we'll plus x squared both sides. I get minus 2x squared. And then the last step here is to get rid of this positive x, it's take away x. Take away x both sides, and you get minus 3x, which is less than or equal to 0. Now normally at this point we could try factor theorem and try and figure out what goes into this equation. You can try 1, try 2, but when all of them have an x, we have a nice easy factor to see. And that is, if this has an x to give and so does this and so does this, we can factor out an x from each term and be left with x squared minus 2x minus 3 is less than or equal to 0. We didn't even have to use factor theorem. Well now, how do you factor a quadratic? We know how to do that. You can do that on the side. To factor x squared minus 2x minus 3, trying to multiply to negative 3 and add to negative 2. Well, there's only really one combo that's going to do that, negative 3 and 1. So we get x times x minus 3 times x plus 1, which is less than or equal to 0. Now let's try and solve that as an inequality. To solve it as an inequality, we need to make a sign interval table. First, let's identify the zeros. The zeros are x equals 0. That would be this one of the solution. Also x equals 3. That's from this bracket. And x equals negative 1. So we'll set up our interval table. That is, we're going to examine this polynomial function in pieces. The first thing we'll look at is the interval, and then we'll decide the sign. It's obviously a cubic, and you could probably, some of us anyway, could look at this cubic and identify already its pattern, where it's positive and where it's negative. But that gets a little harder for some shapes. So we'll make an interval table and say, okay, between these zeros, it helps to list them in order. There go negative 1. I'm going to rewrite it like this. The zeros are negative 1, 0, and 3. So what I want to do is look at the function when you're before the first 0, negative 1, and when you're between the first 0 and the second 0, and when you're between the second 0 and the third 0, and for x is greater than 3 after the last 0. So when x is less than negative 1, sub in something really small and negative, really negative, like negative 10. If you put negative 10 into this, you'll get a negative here from negative 10, and negative 10 minus 3 is going to be negative, and negative 10 plus 1 is going to be negative. So you get a negative times a negative times a negative, which will give you a negative. What about something between negative 1 and 0? Okay, how about negative 0.5? Negative 0.5 here will give you negative. Here it'll give you a negative. But negative 0.5 plus 1 will give you a positive. So you have a minus, and a plus. Those two minuses cancel out. You'd have two pluses times each other, which gives you positive. If you subbed in something between 0 and 3, how about 1? A 1 here would be positive. 1 minus 3 would be negative. And 1 plus 1 is positive. So you get two positives and a negative. That would be negative. And finally, if you subbed in something bigger than 3, like something large, like 100 even, 100 is positive, 100 minus 3 is positive, 100 plus 1 is positive. Since you have three positives times each other, that's going to be positive. So what we've done is analyze this function in pieces between its zeros and found that its negative pieces, which is what we're looking for, where is this function less than or equal to 0? Where is it negative? Its negative pieces are here and here. Therefore, the solution of this function is when this first part, when the function is less than or equal to negative 1 and when the function is between 0 and 3. That also was where the function was below the x-axis, was 0. Last thing we have to do is check to make sure we've got the right symbol here. This function says less than or equal. We always check less than because we don't want to actually check the 0. We want to check between them. But when we write our solution, we say, well, less than -1 worked, but you could actually be equal to -1 according to the original function. So we'll change this to an equal, less than or equal to symbol. Same thing with the second range. You could be between 0 and 3, but according to the original question, you could also equal the zeros, 0 and 3. So our actual solution is less than or equal to -1 and less than or equal to 3, but greater than 0.